Hey guys, what's up? I hope you're enjoying your days off. I just wanted to make a quick video to review some of the stuff that we've covered related to differentiated rate law and integrated rate law. So we'll go ahead and start with differentiated. And what I want to do here is, let me just spell it first, differentiated rate law, is just review like what we could expect would be on a problem related to differentiated rate law. So the first thing that we should remember is that the information they have to provide us with is concentration versus rate, right? They have to give us information on concentration and rate. I shouldn't necessarily say versus. I just think they give us information of concentration and rate, really. So I'm just going to fix that, concentration and rate. Typically, this is written as initial concentration and initial rate. When we're given initial concentration and initial rate, we're going to go ahead and use logic or reasoning to determine the orders. Okay, and remember, we're going to try to keep other reactants constant, and then we're going to see how changing the concentration of one thing affects the rate. And so remember, if we change the concentration of X and the rate doesn't change, it means that the concentration of X has no effect on how quickly this reaction moves, and so then the order is going to be 0. On the other hand, if we change the concentration of X by some factor Y, like we multiply it by some factor Y, and the rate also gets multiplied by some factor Y, then we know that the order is 1. If we change the concentration of X by some factor Y and the rate gets multiplied by Y squared, then we know that the order is 2. I'm going to go back here and add the word order. Okay, so we're going to use some kind of logic or reasoning. And so, again, we need to make sure that when we do this, we are keeping the other reactants the same. So if there were some other reactants, Z, I would want to make sure that Z was being kept held the same. Kept held constant, sorry. Okay, so again, differentiated rate law, they have to give us initial concentration and initial rate. We're going to use logic or reasoning to determine the order. Of course, you should probably practice some problems where there is no option to keep a second reactant constant and how you should handle that. So we did some of those in class. Make sure that you, I'll add that here, like sometimes not possible to keep one reactant constant. So make sure that you review how to logic through that or reason through that, okay? Okay, now what are they going to ask us? They're going to ask us to determine the orders. Remember that you can't just say the concentration of X doubled and the rate doubled, so the order is 1. You have to explain that you understand that it's because both the concentration and the rate were multiplied by the same factor. And with the second order, you understand that the concentration changed, but the rate was actually multiplied by that factor squared. Okay, so make sure you write those sentences. They could ask us for the overall order, which means we would just add up the orders that we determined in part 1. So that if they ask us, that is really a free point, which is awesome. Okay. They're going to ask us to write the rate law. And remember, for a differentiated rate law, it's going to be rate equals K times the concentrations of whatever substances they have. Now, when you write the rate law, you're going to write rate equals K. You don't have to have anything filled in for rate or K. For X, you should have whatever actual reactant it is, and M should be a numerical order. For Y, whatever actual reactant it is, and N should be a numerical order. And if there were a third, you would keep going. Okay, so that's going to be your answer for rate law. Okay, you don't have to show any other work as long as you previously determined how you got the orders. After that, they're going to ask us to solve for K. Remember that we solve for K by choosing the data, like from the data table, one experiment, plugging in for rate, plugging in for concentrations, plugging in for orders that we determined, and solving for K. I do find that students sometimes mess up on their calculator here. The way I type it into my calculator is I type in the rate, and then I divide by this x squared or x or whatever it is. I hit equals, and then I divide by y to whatever power and hit equals. This way it ensures that my order of operations is understood correctly. I do find a lot of students have all the right work, but the wrong answer for K. So just make sure that you're able to use your calculator while there. The other thing is that we have to be able to solve for the units of K. And so that's an area a lot of students struggle. And remember, it's worth its like own point. So remember, the way we would do that is, for example, I would look in the chart and I would see that they were reporting rate in, let's say, molarity per minute. Then I would need to solve for my units of K. That's what's going to go in the box. It's going to be something over something. And then depending on what I determined my orders, let's say I determined X had an order of 2. That would mean that X, which is concentration, shows up twice. Oops, what's happening here? Molarity, because I'm saying that M equals 2. And Y is a concentration. Let's assume it equals 1. N, equals 1. Then I'm going to throw that other molarity right there. And then I'm going to go ahead and say, okay, what do I need to put in this box so that the right side of this equation equals molarity over minutes? Obviously, I have no unit of time, so I'm going to put in minutes. I have 3 molarities up here. That's too many. I only need 1. So I need to cancel out 2 of these molarities. The way I cancel them out is putting them on the bottom of this fraction, molarity squared. And so the unit for K is really 1 over molarity squared times minute, which I could report as molarity -2, minutes -1. And I get that by reporting whatever's on bottom, but if it's on bottom, you have to report it with the negative exponent. So since this has an exponent of 2, I make it -2. Since this has an exponent of 1, I make it -1. And there we have molarity -2, minute -1 as an example for how to solve for K. Make sure that you practice this because there are some problems that award 1 point for K, and that point is the correct value of K with the unit. So if you have the right value but the wrong unit, you might not get the point. On the flip side, I consider it a free point when they give me a whole point just for having the correct unit. Okay, so that's solving for K. Okay, after solving for K, I think the next thing that I often see with the differentiated rate law problem is that they ask some kind of stoichiometry problem. Okay, why would they throw stoichiometry in here? Because sometimes they don't want to use a whole free response problem for stoichiometry, so they just throw it in as part of the other ones, part of a kinetics problem, part of a thermal problem, part of an electrochem problem. So 2 types of stoichiometry. One could be basic stoichiometry, which means they just provide us with some data and they ask us to calculate the moles or grams of something else, or in this case, maybe concentration of something else. Normally, in a problem like this, we can assume 1 liter so that we can use concentration as if it's equivalent to moles. And that's typically what I do in a rate law problem. They're not normally trying to mess with with the moles and stuff like that. So you normally can assume 1 liter. Okay, I'll write that in for most of the problems. Unless they say something specific, you can go ahead and assume 1 liter, which means moles and molarity are going to be equal since it's moles per liter. And if it's 1 liter, then moles and molarity would be equal. For a basic stoichiometry problem, you're going to solve it by either using factor label method, like this dimensional analysis, or you might choose to do what we were talking about earlier this week, which was BCA tables, right? Sometimes that makes it seem a little bit easier before, change, after, and you can check the problems that we did this week to look over how we did that before, change, after. Either way, whichever way you do the stoichiometry, it's going to be great. The second type of stoichiometry problem that they ask us about is a rate stoichiometry. And so what I mean by that, stoichiometry, is when they give us something like, here's a reaction, and the data table that they provided us gives us all the rates with respect to C. But this problem asks me for what the rate is with respect to A. And so you're going to just go ahead and take your rate with respect to C that was provided, and you're going to use the mole to mole ratio to get the rate with respect to A. For some reason, these stoichiometry problems, both the basic stoichiometry and the rate stoichiometry problems, are ones that students miss. And so I'm hoping by reviewing it like this, knowing that it's likely to be asked about, you can kind of remember that, because nothing about calculating these rates is difficult. I find most students just aren't kind of in that mindset because they're still thinking about determining orders and determining K and so forth. Just remember that sometimes they might call it the rate of disappearance of a reactant and the rate of appearance of a product. So just keep that in mind as well, right? Disappearance and appearance. Cool. And then the last thing that they might ask us about is a reaction mechanism. Okay, and with the reaction mechanism, remember you always want to check 2 things. First, you check the stoichiometry. Okay, first you check the stoichiometry, which means you check, does the mechanism add up to the overall reaction? Right? Does the mechanism add up to the overall reaction? If it does, it's a possible mechanism. If it doesn't, then you can cross that mechanism out as not being possible for the overall reaction. So that means you would add up the mechanism and, for example, make sure it matches the equation given, which, like up here, I wrote 2A plus B yields C. Okay? The second thing is you're going to check the rate law. Okay? So that means, does the rate law of the slow step match the determined rate law? So that means the determined rate law of the overall reaction that you would have probably solved for in part A or B or C, you have some rate law that you're going to match. Remember that when you write the rate law of the slow step, you just use the molecularity. So if you have a reaction like 2A plus B yields C as an elementary step in a mechanism, then the rate would be K times the concentration of A squared over B. So I'm not assuming this is my overall reaction. I'm just saying this is like, let's say, step 3 of a mechanism. Then I can go ahead and do that. Remember that we do have the situation of plugging in if we have an equation that involves equilibrium, and I can show an example of that later. I'm going to go ahead and stop this video now because I think I'm limited to a maximum of 15 minutes and I'm at like 14:45. So I'll continue in the next one.